Hi friends, welcome back to my channel. Today I'm planning to solve a very interesting problem from the topic mechanical vibration. This question was asked in Graduate Aptitude Test in Engineering 2024. It's an entrance test back here in India. This problem is so beautiful uh, because the way how it is posed, one, and two, I looked at multiple places on the internet how they have solved it, and none of them really gave me the total idea about the question. That's why I thought, let me do this problem and post its solution on YouTube for better understanding of the students out there. Now, without much ado, let's get started. My request to the audience is that spend some time reading the question. So, here is the question here. You can see there are two massless pulleys. There is a mass, little m, then there is a spring of stiffness 2k, then there is another spring of stiffness k. And here lies the beauty of the problem. Here they are, it's it's essentially a forced vibration problem, because here, as you can see, this particular mass capital A is subjected to a harmonic motion defined by xa equal to a sin omega t. Then they are asking us what is the magnitude of critical driving frequency for which oscillations of this mass, tend to become excessively large. Or, in other words, they are asking us the natural frequency of this particular system. Then, in the question, it is very clearly mentioned that this is an inextensible string. Then, stiffness values are given. Similarly, what this mass values are also given. So, how to go about? Before we get into the maths, let us draw the schematic and understand how the system is going to behave. So, the moment I apply an external displacement xa on the system, what will happen to the spring? There will be a certain load transfer to this particular spring. Let us call that load P. Then what happens? If this point of the spring is extending by xa, then let's say this point is extending by xb. A very valid assumption to make. And let me make it clear, xb is also in this direction. So this is the direction in which I am defining xa as well as xb. Then assume that xa is greater than xb. Then what happens? The relative deformation in the spring will be xa minus xb. This times the stiffness of the spring, which is given as k, will give me the load acting on the spring. Let this be our equation 1. Nothing wrong. Now comes a little bit of kinematics. Kinematics is the study wherein we study the displacements or the deformations by considering equations of compatibility. We won't invoke Newton's second law, we won't invoke other fancy principles, but we just go by common sense. That's the best way to put it. So, here I am trying to use some very basic principles to find out the displacement of this particular mass m when this point is moving by xb. It is simple kinematics. With common sense, we know when this particular point, capital A, moves towards the left, let's say it occupies the new point A prime, then what will happen to this point? This little mass moves by, let's say, x1. Again, x1 is a new thing. Let's say it moves by x1. How to find what is the relationship between xb and x1? It's very easy. They have told us that this string which connects all these things, it is inextensible. That means the length cannot change. It's an inextensible rope. Now let us find the length of this rope from this point to this point. What will be the length? 2s. This distance and this distance. Then let's say there is a half of the perimeter here over the pulley that I am representing as pi r, where capital R is the radius of this particular pulley. Then there is an AB, it is this length, can be thought of as 1/4 of the perimeter of this particular pulley. Now this length of the rope or the string cannot change when the whole system gets deformed by, or when you apply an XA displacement to this particular mass. This point moves by xb, but the length should remain the same. Now what is the new length? New length will be, this length will be what? S minus x1, because initial length was x, this mass moves by x1, so this length is now 2s minus x, like 2 times this length, and this length will amount to 2 times s minus x1, plus this one remains the same, half of the perimeter. Then we have AB here, then we have XB, this particular length. From this equation, it works out like XB is 2 times X1. It's a very important thing. Like what we are finally doing here, we are trying to tell that if this point moves by, let's say, an XB, this mass will move up by an amount half of that. Like x1 was coming to be half of xb. Clear? Again, let me sum up what I discussed over the last 2 minutes. I simply invoked kinematic equations where there is no consideration to the forces. I invoked some kinematic constraints to arrive at the relation between xb and x1. Now let us move to the next part of this problem. The final segment, and indeed the most critical step in this particular problem, is using Newton's second law for this mass little m. Now let us draw the free body diagram. I have already assumed that this mass is moving upwards by x1. So if I invoke Newton's second law, what happens? Mx1 double dot is equal to minus 2kx1. Why? Because it is in the other way, in the other direction, or in fact in the opposite direction. When the mass tries to move up, the spring will resist. But then there is another force which is because of the tension in the rope. Then it is 2p. Why? Because of the configuration on the pulley, the rope is going, so there will be 2p. Then the equation of motion, since it is along the direction of x1, equation of motion will be assuming this particular form. Now we can plug the expression for p with this particular expression. Now here again we can plug in, no more plugins, but let us rearrange these equations. Now we get, this is the equation of motion for the system. It's a single degree of freedom system. If you spend a little bit of time understanding what sort of an equation is this is the equation for the forced vibration problem. Forced vibration problem. Now we want to evaluate the natural frequency. So what's the best way? We need to see the free vibration equation. Free vibration equation is very simple. It is mx1 double dot plus 6kx1 equal to 0. Because in a free vibration problem, there is no external force. Think physically. 2kxa is the term which comes into the equation because of the fact that we are imposing a displacement on the free end of the spring. In a free vibration problem, there is no such displacement which is acting on the system continuously. So this term assumes a value of 0. Now you have the free vibration equation. Now the natural frequency is very straightforward. Omega n is equal to root 6k by m. So let me conclude. I started off the problem assuming that the first spring is in tension. Then I invoked certain kinematic relations, and as a last step, the most crucial and the critical step in solving this whole problem, I used Newton's second law. Then we got the equation for forced vibration problem because it is a forced vibration problem. Then from forced vibration problem, we went back to a free vibration problem. Why? Because our intention was to find the natural frequency. To find the natural frequency of the system, we need to solve only the free vibration problem. Then we reduce the equation to this form, and from this we evaluated the natural frequency. Rest is very straightforward as it involves only plug and check. Now root 6k by m will amount to 6 into 1.5 kilonewton per meter divided by 10 kg. This will amount to, let me do the math, even though it's not that significant, let us do it. It will be 900. I hope my maths is correct. Yes, indeed. Then it will be 30 radians per second. Units are again interest, like very important. So this sums up a very beautiful problem because like there are so many ways you can get this problem wrong. Like if you see the problem for the first time, sometimes we may think, let us assume that the spring 2k and the spring k are in series. So let us say that the effective stiffness will be, let's say, what is 2k by 3. So there are so many ways how we can get this problem wrong. So it's indeed a very beautiful problem. I hope you understood how to do it, and I hope you understood the concepts behind this problem as well. Thanks for watching.